Okay, what ready? Okay, so viscosity. We've spoken about solid friction. So we're talking about viscosity, we're talking about friction that exists in fluids. And if we're talking about fluids, we're talking about two major things. Fluids are either liquids or gases. For example, look at when you pour water, water actually flows very easily. If you pour an equal volume of, say, palm oil or engine oil, does it flow as easily as water does? Not at all, because the viscosity of water is actually lower than that of maybe engine oil, glycerin, and so on and so forth, because the frictional force in water, which is viscosity, is lower, while the frictional force in all these lubricants, grease, engine oil, glycerin, and so on and so forth is actually higher. So viscosity simply talks about the frictional force that exists in fluids, namely liquids and gases. Not only that, viscosity also accounts for certain natural phenomena. Have you wondered when something falls from a very great height, if it hits someone, it can actually bring about a lot of damage? But has it ever crossed your mind, why is it that raindrops that come from several kilometers in the atmosphere, when you are hit on the earth with raindrops, it doesn't cause any damage, isn't it? But if, say, a nail actually drops from, say, 200 meters, you understand what is going to happen. But here we have raindrops dropping from several kilometers, but yet it doesn't do any damage. That is also due to viscosity, because that particular raindrop, remember, we are talking about fluids. Raindrop is an example of a liquid. When that particular raindrop is actually dropping, because of the frictional force in the air, which is gases, in the atmosphere, which is also another fluid, it slows it down. And therefore, by the time it actually gets to the Earth's surface, now the speed has actually been drastically lower. It must have attained what we refer to as terminal velocity. And the law that actually gives the relationship between the movement of an object usually is fair. And if you look at raindrops, in what form are they? They are spherical in nature. So the law that gives the movement of a sphere in a fluid be it either a liquid or in gas, is what we refer to as Stokes' law. Stokes' law. And mathematically, Stokes' law is expressed like this: F is equal to 6 pi NRV. And all of them, for example, F here is talking about the drag force. That's what it means, drag force measured in Newton. We know what this one represents. That's just our pi. And pi has the usual value, either 3.14 or 22/7 mathematically. And then this is what we refer to as viscosity coefficient. Viscosity coefficient. And R is the radius of the sphere, radius of the sphere. And we know V here is the velocity of the sphere, velocity of the sphere. So basically, that is what Stokes' law. Stokes' law tests out the relationship. What happens when a small sphere falls in a fluid, be it a liquid, and is denoted by this formula: F is equal to 6 pi times of the viscosity coefficient, the radius of that particular sphere, and the velocity of the sphere. And by the way, the dimension of the viscosity coefficient at times it could be asked is m raised to the power 1, L raised to the power minus 1, T raised to the power minus 1. That is the dimension of coefficient of viscosity. Let's take note of that. Not only that, we can represent viscosity mathematically like this. You can say viscosity is equal to force times time, that's in seconds, all over the area in meter squared. So which means that if we are asked what the unit of viscosity will be, we can go with 2. The unit of viscosity can be written as the unit of Newton of force is Newton, then time, that's seconds, then per meter squared. So this is 1 unit of viscosity, or we can go with Pascal seconds. Because we know that force all over area alone is what? That's the unit of pressure, isn't it? And we know that pressure is measured in pascals. So either you pascals, seconds. So these are the 2 units of viscosity, either Newton seconds per meter squared or Pascal's seconds. So yes. What about the dimension of viscosity? We can easily get our dimension from this. So maybe we should look at how to get that. Let's put the unit down while we work at seeing what the dimension will be. You can easily get that even from the units. Starting with force. What is the dimension of force? For example, if you don't know the dimension of force, you can simply say your force F is equal to the mass times the acceleration. And we know that acceleration is velocity all over time, isn't it? So, and don't forget that you can now rewrite this one and say this is F is equal to this M, that's M, times acceleration, which is velocity all over time, that's V over T. But don't forget also that velocity is equal to what? That's the displacement, not distance. Speed is different. Speed is distance over time. Velocity is displacement over time. There's a difference between distance and displacement because distance has only magnitude but no direction. So what that makes distance to be a scalar quantity. But velocity is having not only magnitude but also a direction. That makes it a vector quantity. So there is a difference. So displacement all over time. So if we now want to express this in form of this, then we are left with the force now is M. This time around, V is displacement all over time. So we are left with D all over T, then divided by what? This another T. So this gives us M into D all over T. If we change this one to multiplication times 1 all over T. So basically we have F is equal to, then we now have M, that's the M, now into D all over T squared. So if we express this one, we know our mass, the dimension, that's capital M, our D, that's L, and then the T squared, that's T raised to the power minus 2. So we've gotten for F. So we know that our viscosity now is going to give us the force from this formula, that's MLT times minus 2, then times the time is T. Remember, it's like T raised to power 1 all over M. Don't forget that area is length times length. That's right. So which means we have here L squared. So L here can actually cancel one here. So we are left with M. Don't forget, this is L raised to power minus 1 since it is the denominator here. And then this is T raised to power minus 2, this T raised to power 1. So if you had minus 2 plus 1, what does it give us? 3 raised to the power minus 1. So that's that. So if you want to get the dimension for viscosity, that is how we arrive at that. Yeah. It's going to be the same. So instead of check it out, it's the same. It's exactly the same. So that's for that. Let's put it down quickly. So let's talk about factors affecting viscosity. Factors. Don't worry, don't worry. We've not rated, we've not spoken about factors that affect viscosity at all. Factors affecting viscosity. Let's start with number 1, temperature. Now, the effect of viscosity, the effect of temperature on viscosity is in two folds, depending on what kind of fluid we are talking about here. Now, the higher the temperature, the lower the viscosity of liquid. If I want to put that down, the higher the temperature. You can simply write increase in temperature leads to a decrease in the viscosity of a liquid. While increase in temperature leads to an increase in the viscosity of a gas. So that's what I was talking about earlier. The effect of temperature on viscosity will depend on what kind of fluid we are talking about, because fluid is of two folds. Fluid could be a liquid, engine oil, glycerin, grease are all in liquid form. So when we increase their temperature, the viscosity actually decreases. Even look at this. If you look at palm oil, all right, palm oil, when you put palm oil on fire and maybe you want to fry something, by the time you apply it to it, what happens? It actually begins to flow more than it was before, because increase in temperature will have weakened the force of friction, which we refer to as the viscosity here. So increase in temperature will lead to a decrease in the viscosity of a liquid. However, the reverse is the case for a gas. When you increase the temperature of a gas, that will in turn lead to an increase in the viscosity of a gas. So it will be wrong to just say that increase in temperature leads to a decrease in viscosity, because that will be wrong, because increase in temperature does not lead to a decrease in the viscosity of a gas. It is only applicable to liquid. As you can see here, increase in temperature leads to a decrease in the viscosity of a liquid. But since gas is also regarded as a fluid, Because of that, that's why you can't say that increase in temperature will lead to a decrease in viscosity, because that is not actually true for a gas. Because as you can see here, while increase in temperature, when we increase the temperature of a gas, the viscosity actually increase as well. It is only in liquid that when you increase the temperature, the viscosity decreases. So the effect of temperature on viscosity is of twofold. For liquid, whenever the temperature increases, the viscosity of a liquid decreases. But for a gas, when the temperature increases, the viscosity also correspondingly increase as well. So let's take note of this. Let's go to the second one. That's number 2. Yeah.
I don't know if you have heard about a liquid that the surface area solidified, like it had this by the pressure exerted on
Okay.
the surface. I want to especially
There are a lot of liquid. As a matter, there are some solutions that are used by dentists that behave exactly like that. There are some liquid that when you exert pressure on them, it actually hardens them to at least it hardens them, that is by increasing their viscosity. But those kind of liquid are actually used for special processes. For example, in dental, for people who are having dental caries or cavities in them, you can use certain amalgam. Amalgam is a mixture of two metals, for example, maybe sodium and silver, sodium and mercury. Liquid like that actually behave exactly like we are talking about here. So let's look at number 2. Areas. Areas of the layers of the fluid. Areas of the layers of the fluid. Now, let's look up. You will see from the Stokes law the other time, F is equal to 6 pi R. So I told you that R here represent the radius of the sphere. And we know mathematically that area of a sphere is equal to what? 4 pi R squared. So which means that the area here is directly proportional to the radius. What does that mean? It means that as the radius increases, then the area increases as well. And if you look at the relationship between the frictional force and R, you can also see that it's direct. So as F is directly proportional to R. So which means that as the radius increases, the viscosity also increases. So which means that as the area of the layers actually increases, what happens to the frictional force? It also increases, because we know that the area is directly proportional to the radius, and the force is also directly proportional to the radius. So as the area increases, the radius increases, and as the radius increases, so also does the force. So increasing the areas of the layers of the fluid leads to an increase in the viscosity. So when the layers between the fluid are higher, then the viscosity experience between them is going to be high. So the higher the area of the two fluids in contact, the higher the viscosity, and the lower the area of the two fluids in contact, the lower the viscosity as well. And the third one, which is the last one, is velocity. Velocity of the fluid. Yep. Can I explain the area again? Now, let's look at the formula here. That's what will make everything easy. Frictional force is directly proportional from this formula, is directly proportional to R. And what is R? R is the radius of the sphere. And if you want to calculate the area of a sphere in mathematics, you know it is 4 pi R squared. So which means the area of a sphere is directly proportional to R squared. What that means is area is directly proportional to R. What does that mean? As the radius of a sphere increases, the area increases. Let's look at a simple example of that. If you have a sphere, let's say you have a sphere of whose radius is 2 centimeters, then the area of that particular sphere is going to be 4 pi r squared. This time around, 4 pi, then the radius is 2. That's going to be 2 squared, which is 4. Then we now have 16 pi centimeter squared. But what happens if the radius now is increased to, say, 4 centimeters? The area cannot remain the same. Again, because the area now of the sphere now becomes 4 pi r squared, which will be 4 pi. This time around, radius is 4. That's going to be 16. And then 4 times 16, what does that give us? That's 64 pi centimeter squared. So you can see that when you increase the radius from 2 to 4, then the area increases from 16 to 64. So that's what I was talking about. Increase in the radius leads to an increase in the area. That is why A is directly proportional to R. And from the formula we have here, we know that F is directly proportional to R also. That's what we have here. What that tells us is, as the radius of the sphere increases, so also does the frictional force, which is the viscosity, also increase. So increase in the area will bring about an increase in the frictional force or in viscosity. So that's that. So the last one we'll be considering is velocity of the fluid. Velocity of the fluid. And the higher the velocity of the fluid, that is, the more faster the fluid moves, then the lower the viscosity. The faster the velocity, the faster the velocity of the fluid. The faster the velocity of the fluid, the lower the viscosity. So that's that. So these are the factors that affect the viscosity of a fluid. So the next thing we are going to be considering now is, since we know that viscosity is a frictional force that exists in fluid, namely liquid and gases, and we've also spoken about solid friction when we're talking about limiting frictional force, static, which is also called static frictional force, and then kinetic or sliding or dynamic frictional force, and then rolling frictional force. We now want to consider, are there similarities between these two? By these two, I mean viscosity, which is the friction that exists in fluid, and the static or solid friction, which exists in solid. They have anything in common? If they do, what are they? What are the differences between them? Let's start with what the similarities are. Similarities between viscosity and solid friction. Similarities between viscosity and solid friction. There are two major similarities between viscosity and solid friction. Number one is the fact that both of them oppose motion. Both oppose motion. Just like solid friction, we oppose motion. When a body is pulled to the right hand side, the solid frictional force acts towards the left hand side. So the same thing, viscosity also opposes motion. That's why they are called frictional forces. So both viscosity and solid friction oppose motion. And the second one is both depend on the nature of the surfaces or layers. For example, the friction that will exist between a box on a smooth surface, on a smoother surface, will be different from the friction that exists between that same box and a rough surface. The difference has to do with one surface is smoother than the other. The same thing happens. Look at the friction that exists between engine oil, which has a higher viscosity, and the friction that exists in water, which has lower viscosity. So that's that. So both of them depend on the nature of the surfaces. Surfaces for solid friction or layers for viscosity of fluid. Now, let's look at the differences between them. Differences between viscosity and solid friction. So to start with, viscosity occurs in fluid. It occurs or exists. It occurs in fluids. And I've told you what fluids are. Fluids are liquids and gases. Whereas solid friction, even as the name suggests, solid friction exists. It occurs in solid objects. It exists. It occurs between solid objects. That's the number one difference between viscosity and solid friction. Viscosity occurs between layers of fluids, fluids like liquid and gases. However, as the name implies, yeah, solid friction, it occurs between two solid objects, between, say, a box and a floor on which the box is placed, between the tires of a vehicle and the surface of the road. So solid, solid. Number two, it does not depend on normal reaction, whereas solid friction depends on normal reaction. You will recall when I was giving you the various laws of friction. One of the laws of friction that we mentioned was that frictional force is directly proportional to the what? To the normal reaction. So which means that a frictional force is directly proportional to normal reaction. As the normal reaction increases, so also does the frictional force. But viscosity is independent. Independent means that it's not affected, does not depend. So viscosity does not depend on normal reaction, whereas solid friction, on the other hand, does depend on the normal reaction. That's number two. Number three, so another difference between viscosity and solid friction, number three, viscosity actually depends on the areas of the layers in contact. As a matter of fact, it was one of the three factors that affects viscosity that I mentioned earlier. I mentioned temperature, I mentioned areas, and then the velocity. So the areas of the fluid, the layers of the fluid, the area of the layers of the fluid that are in contact actually affects the viscosity. Whereas you will remember, you will recall from the laws of friction that solid friction is independent of the areas of the bodies in contact. So that is another difference. For viscosity, the areas of the layers of the fluid in contact actually affects the value of the viscosity. But for solid friction, the solid friction is independent. It's not affected by the areas of the two bodies that are in contact. Let's go to number 4. Can anybody give us number 4? There's still one more. Apart from these 3, what other difference can you think of that exists between viscosity and solid friction? Exactly. That's right. So that's number 4. Number 4 now. Viscosity depends on the relative velocity. It depends. It depends on the relative velocities of the layers of the fluid. And solid friction, it is independent of the relative velocities of the bodies. So that's the last one, number 4. Viscosity does depend on the relative velocities, that is, the speed at which the two layers of fluid are moving relative to each other. Whereas for solid friction, it doesn't depend on the relative velocities of the one body moving over the other one. So these are the 4 differences that exist between viscosity and solid friction. Just to recap, viscosity, like we all know, occurs in fluid like liquids and gases. And solid friction, as the name implies, occurs between solid surfaces. Number 2, viscosity does not depend on normal reaction, whereas solid friction actually depends on normal reaction. In fact, solid friction is directly proportional to the normal reaction. So which means that as the normal reaction increases, so also does the solid friction. And number 3, viscosity actually depends on the areas of the layers of the fluid that are in contact, whereas solid friction is independent, is not affected by the areas of the two bodies that are in contact. And for number 4, viscosity actually depends on the relative velocity at which the two layers are moving over each other, whereas solid friction is independent, does not depend on the relative velocity at which the two bodies are moving on top of each other. So these are the differences between them. And this, as we've looked at earlier, are the similarities between them. Both of them oppose motion, and not only that, both of them actually depend on the nature of the surfaces for solid friction and layers for fluid. So that's for that. Now let's look at different scenarios in which friction is of importance. We want to look at what are the advantages of friction. And after that, we look at what are the demerits or disadvantages of friction. So let's start with what the advantages of frictions are. Isn't? That's right. Both of them oppose motion. Oh, how does viscosity in fluid? In fluid, like fluid is of 2 types. So which of them? Look, maybe I should use the 2 of them. Listen up. Now let's start with hair. When you let's say you have balloon, why do you think that balloons don't actually fall to the ground the same way that maybe something like a solid substance fall to the ground? Because of air resistance. If you heard about air resistance before, what the name of air resistance? That's viscosity, isn't it? Exactly. Most of the time you see maybe light objects like nylon and so on and so forth, they actually take time for them to get finally settle on the ground because of air resistance. That particular air actually opposes their downward motion because everything is acted upon by force of gravity. Eventually, they come down. But for lightweight substances, the air friction, the viscosity in air, actually slows the rate at which they are moving down. And even at the beginning, I told you about raindrops. Why is it that raindrops is coming from several kilometers and you expect them to be accelerating downward? And by the time they get to the air surface and hit anyone on the head, you expect a very, very high impact. But that doesn't happen. So why is it that raindrop is not injurious or harmful to humans, even though they are coming from a very great distance? That's because of the viscosity of the air. The air actually, exactly, it's called air drag. The viscosity of the air actually slows it down and ensure that it reaches terminal velocity by the time it gets to us air. So if it lands on our head, it doesn't cause any damage to us. That is one of the applications of air viscosity. Now, what about fluid? Now, if I think about fluid, for example, let's say you have an engine oil. If you drop a body into it, it doesn't sink just direct, it doesn't sink easily to the bottom of that particular engine oil the same way is going to happen in water, for example. Why? Because the viscosity in engine oil is more viscous than water. It slows it down, all right, and ensures that it goes down gradually. It doesn't go down as fast as it would, as if you are dropping this. If you drop this now it falls very easily because the viscosity in air, the air drag is actually lower. But if you drop this same thing into glycerin, for example, it actually falls slowly because the viscosity in that particular fluid, in that particular liquid, actually slows it down. So that's that. Another question? Mm-hmm. Okay. Okay. Mm-hmm. Okay. Okay. Well, that one is different. Now, if a person, let's say, a person falls and lands, even look at when people are doing all these long jump, all right, or high jump, most of the time, you see all these pole vaults in games. In pole vault, there is always foam, isn't it? All this elastic material. At the other hand, they land on it. So it doesn't matter if you are landing on your back because that particular foam actually cushions the effect. Remember, when you land, your weight acts downward, and then an opposite reaction actually acts upward. That's why if you jump down, you feel a jarring effect on your body because as your weight is acting downward, then a normal reaction also acts upward. So a person who falls down over a hard surface, maybe a bare floor, concrete area, can actually get injured because of that particular jarring effect due to the reaction that he or she experiences. But if a person falls into water that you are using as an example, remember fluid, under fluid and pressure, there is what referred to as upthrust, isn't it? When that particular person falls and lands in water, the person experiences an upthrust. And you know what upthrust is, right? For example, if you are trying to draw water from a well, when that particular bucket is still submerged in water, it feels lighter, isn't it? But once it leaves the water, it's as if there is more water in it than when it was there because it suddenly feels heavier in the hand. So what happens when it is still in the water? When it is submerged in the water, there is upthrust on it, and because of that, it appears. You could call it apparent weight. It appears as if it is lighter, and the same thing happens when a person lands in water. Now, there is that particular upthrust that happens, and that actually helps to cushion the reaction that particular person feels. The person can only just feel some impact due to that particular water, but because the upthrust actually lowers the amount of reaction that particular person will have gotten, had it been that you are talking about a hard surface, the person is going to actually feel a lot better. And the same thing happens when you're using all these foam because they provide that particular cushion. They actually lower That is when you land on a foam, for example, a cushion material, it actually lowers drastically, almost to the barest minimum, the reaction that you would have experienced, which is always in opposite direction to your weight. And that is why the bigger a person is, the higher the reaction that are going to be, because a person who is bigger is actually going to have definitely a higher weight. And don't forget that that particular weight is going to be equal and only opposite to the normal reaction. So that's that. If you are landing in water, landing in a fluid, landing on a mattress or any cushion material, it actually lowers the effect of the reaction that will be felt. And because of that, you won't experience the jarring effect that you will have felt had it been on a hard or a harder surface. Another question? Mhm. Does not at all. It doesn't. It only affects the lubricant. If you apply temperature to two bodies, let's say you have a grinding machine now, and you put that particular grinding machine, you put it under direct sunlight. Don't forget that grinding machines are always lubricated by using all these maybe grease and so on and so forth. Now, the sun can actually melt that particular grease, and then some of it actually get washed away. And because of that, the friction in that particular body part will increase, but not because of the temperature, but because that particular heat has affected the viscosity of the engine oil. But temperature has no direct effect on a particular solid friction. Although liquid, for example, imagine on a wet road, let's say rain fell. Now, when rain falls, drivers are supposed to be more cautious. They are supposed to actually lower the amount of speed, because when rain falls, everywhere is wet, including the road surface, and fluid always reduces friction, isn't it? So when that particular driver mashes the brake, the car doesn't come to a stop the same way it would have come to a stop on a dry, exactly on a dry surface. So that's that. Another question? Mhm.
Similar to this question.
Okay.
So why is it that when it's raining, running it feels as though you are being flogged?
Well, even let me make it two scenarios here. Now, let's say it has begun to rain, and then there is rainstorm and wild wind everywhere. You notice that when you are running, it makes this very, very difficult, because it's as if you are being pushed back, isn't it? That's the air friction. That's the viscosity we're talking about here. It's raining, there was wind everywhere. You are trying to run. You won't be able to run as fast as you would, because as you are running in the forward direction, the frictional force, which is the viscosity in the air, is acting in the opposite direction. It's as if somebody is pushing you back. And to answer is question when you are running, actually, is different from when you are stationary and then raindrops are actually coming to you. You are moving with a certain velocity, and because of that, the impact on the raindrop on any part of the body is actually more significant than when you are stationary. For example, let me give you an example. If you have a car parked and then another car is moving and rammed into it, the damage is actually going to be lesser compared to if the two bodies were actually moving with certain velocity towards each other, isn't it? Exactly. That particular raindrop is moving with a certain velocity. You are also running with a certain velocity. So you expect the impact to be more felt than when you are stationary. And when you are stationary, you have no velocity, isn't it? And that particular raindrop is going to only moving with a terminal velocity. So that's for that. Now, let's look at what are the advantages of friction. Advantages. Advantages of friction. Number one, friction makes walking possible. Friction makes walking possible. So let's look at the first one. There are several advantages of friction. One of the advantages of friction is friction makes walking possible. Without friction, if friction were absent, it would have been impossible for someone to actually continue to move and then to stop when he or she decides to stop. Because it is the friction between either the sole of the feet of a person who is not wearing any footwear, or between the sole of that particular footwear and the surface of the floor. Imagine that there are no friction. Sleeping will be very easy. You know what sleeping means? At least we actually make it easy for people to actually fall easily, because there's not going to be anything that actually help to create a sort of firm contact between the surface and the sole of that particular feet. Not only that, friction actually enables us to be able to stop when we are moving. Imagine that there's no friction, and then an object in motion will continue endlessly in motion because there's nothing to actually put it to a stop. For example, you have if you throw something on the ground, let's say you throw a ball on the ground, that particular ball will not continue to move forever, isn't it? At a point in time, without anybody stopping it, what happens? It stops. What do you think is responsible for the stoppage? The friction between that particular ball and the surface of maybe the football field or even a concrete floor. So friction makes walking possible because the friction that exists between the sole of the feet and the surface enables that to happen, and it prevents or lowers chances of slipping. As a matter of fact, one of the reasons why it is more easier or more likely for a person to slip when you have, if you are talking about a concrete floor, imagine we are talking about a tiled room floor. Now, care has to be taken. If you are moving on a tiled floor, for example, especially if somebody has maybe spilled water on it, that increases the chances of a person falling, isn't it? Not because there's no friction, but because the friction has been reduced. By what? By that particular friction. I told you a while ago that fluid actually decreases friction. That's why a car on a wet road is going to find it more harder to come to a stop than a car moving on a dry road. The same thing when water is spilled on a floor, usually a tile floor, because you know that tiles by nature are tiles by nature, are they rough? No, they are smooth. And you know that the more smoother a surface is, the lower the friction. That is why it is easier to actually experience a fall on a tiled floor, especially if it's commanded by water spillage, for example. But even though on that particular tiled floor, we are still able to walk because friction, at least small amount of friction still exists that makes walking possible. Let's look at number 2. Friction makes it possible for cars to come to a halt when brakes are applied. When brakes are applied. Now we know that it is friction that enables cars to come to a stop when the driver applies the brake, either suddenly or purposefully. Now you are in a vehicle, a commercial vehicle, for example. When you get to the place where you want to alight, you tell the driver, I am alighting here, and then he mashes the brake and the car comes to a halt. That is only possible because there is friction between the tires of that particular vehicle and the surface of the road. What do you think will happen if there are no friction? That particular car, even though you match the brake, but because there is no friction, which will have brought that particular car to a halt, that particular car continues to move forward because the tire continues to roll, and that particular one, at least that brings about the car being in constant motion. So friction makes it possible for cars to come to a halt when brakes are applied. Let's look at number 3. I'm coming. Friction enables nails and screws to remain in position. Now we know that nails and screws are used to hold certain things together. For example, all these furniture makers, at least they hammer nails into wood, isn't it? So why is it that these nails stay put in this wood that they don't, at least when you nail it in, it doesn't come out? As a matter of fact, when they nailed it in, even if you want to remove it, it will require considerable amount of force for that particular nail to be removed. Why do you think that is? Why do you think that is? Because when you hammer that particular nail into place, there is friction between that particular wood and that particular nail. So that's why it requires force for you now to remove it. So it is friction that enables nails and screws to remain in position. For example, what enables particular nail to stay in position is the friction that exists between the nail and then the inside of that particular hole in which it was actually hammered into. The same thing when you apply screw. All right. As a matter of fact, if you look at screw, you see that they have threadings, isn't it? Screws are never smooth. And those threadings are there to do what? To increase the friction between them and the surfaces into which they are drilled into. So that's another example. Okay. Okay. And no, it's when a car is moving. Remember that there is something called inertia, isn't it? So imagine a person wanted to alight from a car, but too impatient to wait until that particular car comes to a full halt and attempts to come out the same way you are trying to describe it now. For example, you want to come out from a moving car. You are not in control of your mobility and your movement, isn't it? Because now you are in a car. That particular car is moving with a particular velocity, and you are attempting to come out of it. So you expect that the resultant effect of the force of that particular car is actually going to upset your own equilibrium. You can only walk under normal condition when you are in a state of equilibrium, and you can only be at equilibrium if there is no external force acting. Even that's the meaning of equilibrium, isn't it? When there is no longer any external force acting on you, but attempting to come out of a moving car, you have an external force, which is talking about that particular car acting on you, and that will definitely affect your stability or equilibrium, if you will.
And there are two things now for when someone somebody uses the brake during high speed.
Go ahead.
It's either the tire switches on the floor or the car stops.
What skidding? Now, when you apply brakes, cars will only skid under two conditions. For example, if you are moving on a at least on a level ground, you are not maybe negotiating a bend, and your speed is not too high, a car will come to a stop, will come to a halt without skidding. But if a car is moving at a very high speed, now you expect that that particular car, first of all, slow down before applying a brake to bring it to a stop. But imagine a person who is moving at a high speed and all of a sudden applies a brake. You don't expect that particular car to come to a halt normally. Number one, it can skid. That's why you can see car leaving the road, even moving over the gutters, isn't it? Because it can actually skid, it can undergo translational motion. Not only that, it can even, because of inertia, isn't it? It can actually somersault as a result of that. So you expect any sensible driver that is moving to actually, number one, maintain a reasonable speed, and when he or she now is attempting to come to a stop, gradually slow down before applying the brake to bring it to a complete halt. But when a person is moving at a high speed and at the same time wanting to bring a car to a sudden halt, that will not happen because of imbalances in the forces acting on that particular body. And the second one is, imagine a person trying to negotiate a bend, isn't it? We call it, that's one of the reasons why roads are banked. You understand what banking of road is? If you are moving on the road, and when you get to an area where you have these bends, isn't it? You will notice that during road construction, at those bends, the roads are actually more widened than under normal level ground, because under normal condition, drivers are supposed to move closer to the right hand side before negotiating that particular bend. In banking of road, at least you see this formula: tan theta is equal to v squared all over rg, where this theta here is the banking angle. That is equal to banking angle, where v is the velocity with which that particular car should be safely moving to prevent it from skidding, where r is actually the radius of that particular road, and g, of course, is acceleration due to gravity. So if a car is moving at a high speed, and let's say the driver is not used to that particular road, he doesn't know that that particular road ahead, just shortly ahead, is a bend that needs to be negotiated, and the same speed with which he was moving, now he suddenly encounters a bend, and if he attempts to use that same speed to negotiate that particular bend, what happens? He skips away. As a matter of fact, if he attempts to move like this, then this car moves in the opposite direction. That's a simple law of inertia. So that's that. And that is why roads are banked at all these corners, to ensure so that a driver actually moves outside and then negotiates inward, so that that particular centripetal force maintains that particular car and prevent it from skidding. So that's for this. We can give us two more to make it 5. Number 4. What other functions of friction do we have? Yes, that's right. So that's it. So let's put this down. Just wait a bit. Friction. Friction is applied in grinding and sharpening of objects like cutlasses. For example, when a person buys a cutlass and intends to sharpen it, what does the person do? The other gets, at least there are all these sharpening machines. You put it against it, and then the friction between that particular cutlass and the sharpening machine actually ensures that it is sharpened. And not only that, even the normal knife we use at home, if you notice that it is blunt, what do? We can look for a stone, and then we just rub it against it, and then it becomes a little bit sharpened. Not only that, what about in generating electric? I think what about in generating charges? Because friction is also used in generating charges, isn't it? That's one of the ways. For example, before the advent of matches and so on and so forth, when people want to actually make all these fire, what do? They get something like a stone, then get a cutlass and begin to strike it. And what happens? Then sparks are generated. What do you think brings about the production of those sparks? That's the frictional force between that cutlass and that. Not only that, it's also used in grinding machine. Why is it that people who have grinding machine, when they get a particular stage, they notice that whatever is it that they are grinding does not become easily ground, isn't it? Anymore. So what do? They remove that, take it to that particular, take it to people who will help them to reinforce exactly. So it is friction that will be used in generating those particular threads again, so that whatever is it that they want to grind actually become ground easily. Not only that, let's say people who are grinding pepper, even using the normal, at least using this and exactly using maybe stone. All right. Now, at times, what do? They get like small pebbles, isn't it? They break it on that to actually increase the friction. They wash it away before doing their grinding, because if the stone surface is smooth, it's going to take longer time for that particular pepper or whatever it is that they want to grind to actually be well ground. So that is one. You can give us one more to make it 5. One more. There are still other applications apart from these 4 that we've mentioned so far. What other applications of friction do we have that we've not yet mentioned? Anybody? Okay, so let's number 5. It is used in conveyor belts. You know what conveyor belts are? Okay. Friction is used in in conveyor belts for transferring or carrying objects from one place to another. Now, conveyor belts are special belts that are used often in industry for transferring or carrying objects from one place to the other. For example, let's look at the Dangote cement making factory in Obajana in Kogi State. Have you asked yourself, all these several thousands of bag cements, do you think that they are being carried on the head or by people from where they are backed to where they are stored? Not at all. How many people do you think will be needed to do that if you are to be manually or mechanic, or if you are to be manually done? So when they are backed, they are placed on conveyor belts, and conveyor belt can actually move 100 at a time. It moves it from that particular place to where they are stopped. They are even falling themselves, so they don't need anybody carrying them and placing them somewhere. So conveyor belts are used in transferring or carrying objects from one place to another, especially heavy objects. Next. That's right. That's it. That's a very good one. Friction also makes gripping of objects to be possible. As a matter of fact, without friction, it would be difficult for certain objects to be held or gripped, isn't it? Exactly. So we've spoken about 6 advantages of friction. Now it's time to shift our attention to the demerits or disadvantages. These advantages of friction. Because normally, anything that has an advantage most often do have a disadvantage. So let's look at some of the disadvantages of friction. Number 1, it causes wear and tear. It causes wear and tear in objects and machines. Not only that, it causes heat. It causes excessive heating. It causes excessive heating in machines. And number 3, it reduces efficiency of machines. It reduces the efficiency of machines. And number 4, it wastes useful energy. So let me explain one after the other. These are the 4 main disadvantages of friction. Number 1, it causes wear and tear. Look at cars. When you buy a car tire newly, the threading are actually very, very pronounced. But the more you use it, what happens? It begins to become worn out. As a matter of fact, it can get to a stage where even the wires that were initially present is now visible outside. That is wear and tear. Not only that, imagine a person, all right, who wears, say, a trousers. Imagine children, whenever they maybe when they go to amusement parks on carousel, when they are sliding down. If they do that consistently, what do you think will happen to the cloth that they are wearing? It begins to thin out, and if they are not taken, you will see that it begins to tear or even holes appearing from there. So it causes wear and tear. Not only that, it causes excessive heating in machines. Even apart from machine, if you have your 2 palms together and you begin to rub it, after a while, what happens? Then it generates heat. Now imagine what will happen in the various parts of machines that are in constant motion, because some machines are operated for hours. If you rub your palm for just 10 minutes, you can generate the amount of heat. You can see the amount of heat that's generated. Now imagine a machine that's operated not for 1 hour, but almost for 24 hours. Now look at the amount of heat that will be generated as a result of that. Not only that, then we look at cars. Why do you think that cars needs a car radiator that will cool it? Because some of the moving part of that particular car, what happens to them, they actually generate friction, and because of that, the engine of the car can actually become extremely warm or even hot, and we need to be cooled down by conventional current, which exists in the car radiator. So one of the disadvantages of friction is it causes or produces excessive heating in machines. Number 3, it reduces the efficiency of machine. Now, a machine in which there is no friction, the efficiency is what? 100%. But you and I know that there is no machine that has completely 100% efficiency, because friction always occurs. And whenever there is friction occurring in a machine, that will lower the efficiency by any number. So that's why efficiency of machines, of ID machines, of normal machines are usually 90%, 80%, and so on and so forth. What reduces the efficiency of machine is friction. Why? Because remember, the work input, when the work input into a machine is equal to the work output, then the efficiency will be 100%, isn't it? If the work input is, let's say, 50 joule, and the work output is 50 joule, the work you put into that particular machine is 50%, and the work output produced by that particular machine is 50 joule as well, then the efficiency is 100%. But most of the time, some of the work input will be used in overcoming friction. So if you have a work input of 100 joule, and 20 joule out of the 100 joule was used in overcoming friction in the machine, now what is the work output now? That's 80 joule. You now have 80. Efficiency is work output all over work input multiplied by 100%. So now the work input was 100 joule, but 20 joules out of it was used in overcoming friction. So which means the work output now is 80 joule. So that becomes 80 joule all over 100 joule multiplied by 100%. That gives efficiency of 80%. So you can see now that the efficiency has been reduced. So another thing that friction does, which is a disadvantage, is it reduces efficiency of machines. And not only that, even from what I've explained here, it wastes useful energy. Energy that should have been used in doing work is actually used in overcoming friction. Energy is supposed to be used in doing work, but some of this energy will be used in overcoming friction. So which means there is lesser amount of energy available to do the actual work for which it was meant. So it wastes useful energy. Now let's look at ways of reducing friction. What are the ways of reducing friction? Yes? We're going to have a break when it is 1. Wow. Let's just talk about ways of reducing friction, and then we have our break. Let's look at that very quickly. Yeah. You said? Boxes. Okay. Not at all. It's basically because of this. Number one, the closer you are to the wheel. Remember, if you're even sitting, say you feel more heat because you are actually closer. Remember, all the tires also generate heat due to friction. And not only that, it's due to ventilation in that particular car. There are some cars that it doesn't depend where you sit, you'll be fine. Ways of, very quickly, let's round it off. Ways of reducing friction. Ways of reducing friction. Number one, by lubrication. By lubrication. Now, there are some materials that have high viscosity. They are called lubricants. And we have two types of lubricant. We have lubricants that are in liquid form. We have lubricants that are in solid form. For example, glycerin is a lubricant. Grease is a lubricant. Engine oil is a lubricant. Even, at least before the advent of all these modern lubricants, even palm oil are sometimes used as lubricants. So liquids that have high viscosity are used as lubricants because all these lubricants will reduce the friction that exists between the moving surface. If you look at a grinding machine, for example, most of the time you notice that they are always oil. The moving parts of them are oil by using grease so as to reduce friction in them so that they don't become excessively hot. Because after all, we said that one of the disadvantages of friction is excessive generation of heat. So lubrication, application of engine oil, glycerin, grease is one of the ways of reducing friction. Number two, we can use ball and bearing by using ball bearing ball bearing. Now, ball bearings are usually in spherical form, and you have them in the wheels and axles of machines. All right, they are there so as to reduce friction due to the motion in those machine or engine parts. And number three, streamlining, by streamlining. Now, streamlining is talking about when the shape of objects are positioned or designed in certain ways. For example, if you look at fish or fishes in motion, that is in water, the head are usually pointed, isn't it? They don't have flat heads because if the heads are flat, that will actually create a large surface area, isn't it? And I've told you, the larger surface area, the higher the viscosity, and the more difficult it will have been for them to be able to move. But the heads are pointed, and because the heads are pointed, the surface area is what? Is lower. And the lower the surface area, the lower the viscosity or the frictional force. Not only that, look at aircraft. If you look at the tip of aeroplanes, what refer to as the nose cone, they are always pointed, isn't it? So as to reduce the frictional force, the viscosity in what? In air when they are flying as well. So objects are made as streamlined, the bodies of objects are streamlined so that when they are moving, they actually have very little amount of frictional force. Not only that, look at bullets. The bullets in guns, are they made flat? No, you can see that even the edges are what? Are pointed so that when they are ejected from these guns, remember they move in air before getting to their target, so that the air friction will actually reduce. So that is the meaning of streamlining. Give us one more to make it four. By painting, that's right. By painting. So most of the time when you painting certain parts of an object can actually reduce friction between that particular part of the object and another moving part. So these are the ways of reducing friction: by lubrication, application of grease, of maybe glycerin and so on and so forth, by using ball bearing, by streamlining, and also by painting. So let's go for a break. Then we come back by, how many minutes do you need for your break? Hey, there, you can start, huh? All right. And Victor, please come.